All right, welcome. Welcome to CS208E. Who saw this on the course schedule and went, what is that course? I've never heard of it before. Yeah, exactly. So let me tell you a little bit about it. First of all, my name is Chris Gregg. I'll have more on me later, a little bit later. I recognize a whole bunch of you from various other classes, 106B or 107 or 107E. So welcome to another class. I guess I didn't scare you away, so that's promising. Um, and this class is originally designed by Eric Roberts. Does anyone take a class from Eric Roberts at all? A couple of you guys. Did you take 106A maybe from him or some other class?
No, it was Thinking Matters.
Oh, Thinking Matters, yeah. So Eric Roberts was a professor here. He's a professor emeritus now, and he is kind of extremely well known in the field of computer science education. And this year he actually did retire, and now he's up in Portland, Oregon, teaching at Reed College up there, and they're very lucky to have him up there. But this course is designed for him, so most of the things you're going to see in this class were influenced by him. I have put kind of my little take on a lot of it as well, but should you ever meet Eric, you can say, hey, I took your class and Chris Gregg taught it, and blah, blah, blah. You can give him full credit for that part of it. But what is this course? Well, this course is part history of computer science. You know, one of the things about computer science, as opposed to, excuse me, I'm battling a cold that's going around. As opposed to a lot of other fields, is that when you take math in high school, you take physics in high school, you end up talking about a lot of the people that created a lot of the topics that you're talking about. You guys know who Isaac Newton is, and you know who Einstein is, and you have probably heard of Euler, and you've probably heard of some of these other big Gauss and so forth, right? There are probably not many computer scientists that you actually know, right? And then hopefully there's a couple that you hopefully know, but in general, one of the things that this class is going to talk, we're going to talk about the various people involved in the history of computer science, and the ones who really were the brains behind why we have computer science today. Okay, so that's kind of the framework of this. What's the class going to involve? It's going to involve a lot of historical kind of information, but put in context of what was going on in the world and what was going on in computing at that particular place. World War II, which comes up in pretty much every discipline in the entire planet, is critical to some of the things that have gone on in computer science because of the Enigma machine, which was a encoding machine that the Germans used during World War II, and there was a group at Bletchley Park in Great Britain that needed to break some codes, and there was some pretty good computer science that was done in order to figure out how to break those codes and ostensibly win World War II. By the way, so I'm going to talk about this later as well. I was in the Navy for a number of years, and every group in the entire Army, Navy, Air Force, whatever government organization has their story about why their community won World War II. And so this is the computer science reason about why. Come on in. About why we won World War II. But that's that. So anyway, that's what this course is about. Okay, there are only about 20 of you. There may be a few other people trickling in and out. We purposely made this relatively small, but we also opened it up to the whole entire school, which is why. And I actually did that late in the game, so that's why you might not have seen the course even pop up at all. But that's what we're going to be doing mostly. Here are some of the topics we're going to be talking about. Now, some of these things you have seen before. Who's taken 107 or above in CS classes already? Okay, so guess what? You guys already know a little bit about binary arithmetic, right? You guys already know a little bit about digital logic. Maybe not quite the digital logic. Any double E's in here? Yeah, you probably know a little bit about digital logic at this point, right? So we're going to get some topics in here that if you have seen before, but you may not have seen some of the history behind some of that. You may not have seen some of the ways we teach some of these things in terms of some of the pedagogical things we talked about. And what we're going to do in this class is, because there's such a wide range of people. There are any freshmen here? No freshmen here. I thought there were a couple on the roster. But if you've never taken any CS, or you're kind of brand new to CS, this class is also for you. And maybe you don't even know what digital logic is or binary arithmetic. That doesn't matter. What matters is that you're willing to listen and learn about it. And we're going to have basically two assignments in many cases. One for people who are like, I already know about all this stuff. I'm going to go to do this other assignment, which is the more advanced, like thinking about it in a little broader perspective, versus the people who are brand new to this, going, yeah, I kind of want that. Like, I want to do some of the 106A Carroll problems that you guys all did or have taught before. I see some SLs in here who taught before, and you're probably not going to want to like solve Carroll problems because you already know how to do those. But if you've never even heard of Carroll, great, you can do that part. If you have done that before, you can do the other assignments. So we're going to do that as we go along. We're going to talk about a lot of these. I'm not going to go through all the details about this. We are going to have at least one guest lecture by, speaking of the Enigma machine, a guy who calls himself Dr. Enigma, and he's all about the Enigma machine. And he has put together a big lecture about that, and he tours around the country and talks about that. And he will bring an actual Enigma machine. By the way, if you go look them up, they're like, hundreds of thousands of dollars to purchase. Because they're kind of rare these days. But he will do that, and he'll talk about all the details of that. And then we're going to keep going through here and talking about all the big things that you may or may not already know something about. Okay? So the other thing about this is we're gonna give you the opportunity to also talk about some of these things. If you happen to be an expert in cryptography because you took a couple cool cryptography classes, talk to me and we can roll you into maybe some of these lectures and talking about some of these things. I am not an expert in all of these things, right? I wish I was, but I know enough about them to probably talk to you about them, but I'm not an expert in all of them. So that's the overview as we're for the actual class. Now, who are we? Well, my name's Chris Gregg. I'm going to talk a little bit more about myself in a minute, and this is Ben Allen. And Ben is actually he's graduating this year with his master's degree in computer science, although he already has a PhD in communication.
It's modern thought and literature.
Modern thought and literature. Well, anyway, modern thought and literature. And Ben is in a program that we are starting, or that we started a couple of years ago, that is trying to increase the number of computer science instructors around the world, thinking that there are lots of people with PhDs who want to teach, but there aren't very many jobs in their fields. Why not give them some computer science skills, because they're probably already good teachers, at least we hope they are, and teach them enough about computer science to be able to teach intro classes and at least some computer science. So Ben is doing that. He actually happened to have written his PhD thesis on the COBOL programming language. So he does know a little bit about that, and also has an associate's degree in computer science from way back in the day too. Sorry, I'm dating you. But that's who we are. Ben is going to be the head TA. If you have logistics kinds of questions, probably Ben's the one to go to. Although this class is small enough that you certainly can email me directly and just ask whatever questions you have as well. So that's Ben. Do you want to say anything else about yourself?
That's it. I saw people cringe thinking about writing a dissertation on COBOL. It was a strange idea. I think it worked out, but.
Well, it certainly worked out because you got a piece of paper that says you have. But whether or not it was fun experience is a different story altogether. Okay, who am I? If you've taken 107 or 106B with me before this, you've seen this exact slide. I just rehash it every time I teach a new class. But I got my undergraduate degree in electrical engineering from Johns Hopkins University many, many years ago. And then after I graduated from college, I went straight into the Navy. And I spent about 7 years on active duty in the military. Got to see lots of places in Southeast Asia and the Middle East, and spent plenty of time on various ships and a submarine or two here and there. And I was actually a cryptographer or a cryptologist, I guess is what they called us when I was in the Navy. Nowadays they call it information warfare, which I think is a little silly. I think I'd rather be called a cryptologist, but whatever. I did that for about 7 years and then spent 14 or so years in the reserves and retired a couple years ago. And I'm kind of glad it's behind me now, for what it's worth, but it was a good experience. After I got out of active duty, I decided I think I want to go be a teacher. So I went and got a master's degree in education and ended up teaching high school physics for about 7 years. Does anybody have their favorite teacher ever was a physics teacher? Yeah, a few of you. So I mean, this happens, right? Physics teachers we love to teach and we love all the demos and it's a fun. Well, some people don't love it, but in general, I love teaching physics and I thought it was great. I did that for about 7 years and said, I think it's about time for me to go get a PhD. And so I did that and ended up at University of Virginia, got a PhD in computer engineering, and which is kind of at the in between computer science and electrical engineering. So that was kind of cool. And then I ended up teaching computer science at Tufts University outside of Boston for a few years, and then landed here in 2016. So I like to say that I'm a junior. So with no graduation plan at this point. And you can go and look at my website if you want more information about me. I have an obligatory picture of my two dogs. This is Juno. We just got Juno last week, and she's still a little bit shy. She's 2 years old. We got Jupiter, who's the outgoing one, and he's just a puppy at about 7 months old. And then we love taking them around. I was telling somebody earlier that Juno is from Florida, and we live up in Pacifica, and it's cool, very cool up there. And she does not like the cold right now, so we're ordering her a little sweater, and we'll see how it goes. So, anyway, that's that. Let's talk about logistics for a few minutes about this class. There is a website. In fact, I have to make one quick update. Ben found a typo in our syllabus. Mm-hmm. Yeah, we have to make it about when the final day is. Well, don't download it right after or until after class when I push the changes. There is a textbook for the class which is available on the website as a PDF. I think it's called a course reader, but it's really a textbook. And you absolutely need it for some of the assignments, but you can use it in PDF. You don't have to go buy it. Should you want a paper copy, I think the bookstore has them. Has anybody ever been in the bookstore? This is probably not a thing anymore. There you go. But you can get it either online or in the bookstore. And it's very well written, and it's very cool. And all the topics we're going to talk about are covered in more detail in the book. This class has some participation credit. And weekly assignments. We've got some assignments, and we've got class presentations, which we're going to talk about. We're going to have to talk about the details of when you guys are going to do some presentations, but we'll sprinkle them throughout the course. There's enough of you here that if for some reason you don't all get to stand up here during class, then it's not like it's going to affect your grade just because you couldn't get a chance to do that. We'll work on that. And there is a final project. And the final project is going to be team-based, and it's going to you have to find something interesting about computer science, either history or some big idea that we probably didn't cover in much detail in here, and talk about it. And so I think the final project is going to be kind of fun. It's kind of up to you and open-ended to the extent that you can basically teach us something about computer science that we don't know already. That's related to some big idea. And it can also be some sort of history-based project or whatever. Or if you want to do comparisons of big programming languages over years, up to you. We're going to be very flexible about those final projects, but that's going to be worth part of the grade too. What this class isn't, close the door so people don't storm in here, it's not like 107 rigorous kind of course, okay? We're not talking like, we're going to have weekly assignments, and they are probably not going to be the thing you spend the absolute most time on during the week, okay? I'm not trying to make this class into some hardcore, really intense class. I want it to be fun, I want it to be interesting, and I want you guys to learn a bunch of things, and I don't want you to think, oh, why did I take that hard? That's not the point of this class, okay, for what it's worth. And I think the grades will probably be relatively good should you put in the work to do the assignments and projects and so forth. We'll leave it at that. Okay. Before we go into the game, what questions do you have so far about this course, or about me, or about Ben, or about this hot room that we're in, or what? Anybody have any questions at this point? Okay, let's do a little survey before we do this. Sophomores. Okay, a few of you guys. Juniors. Okay, only one. Amazing. So, seniors. A few of you. Okay, graduate students. A whole bunch of you guys, graduate students. So, again, do not be worried if you find yourself, you're like, oh my God, how can I compete against all these people in various groups? That is not the point of this course. We will all learn together. There is nothing tremendously rigorous and tremendously there's a lot of things that will blow your mind, I hope, about some things. Especially if you haven't seen Turing machines before, and P versus NP and those kinds of things that you've probably seen in other classes. We'll talk about that and how it came up historically, who was responsible and so forth. But okay. All right, let's play a little game. Who invented the difference engine? Yeah.
I think Charles Babbage.
Charles Babbage. Now, the question is, what's a difference engine? We will talk about that in a few minutes. But this guy, Charles Babbage, now, we're talking about a history of computer science here. Notice when this guy was alive. 1791 to 1871. that was a while ago. Okay, 1780 or 1800s was when Charles Babbage was thinking about computing, and this is a big deal that he was thinking about it back then. He created this thing called the difference engine, which we're going to learn a little bit about in a few minutes. And he never actually got his difference engine to work. It was like before its time in many ways. But he created that, and this is much farther back than a lot of people think computing was happening. Had he gotten it to actually work, we might be another 100 years ahead in computer science. That's the way it goes, I guess. But that's that. All right, who is often described as the first computer programmer? Yes.
Ada Lovelace.
Ada Lovelace. Okay. Has everybody heard of Ada Lovelace? I hope at this point you have. Ada Lovelace was friends with Charles Babbage, so we're talking about the same time period in history. Okay, and she's known as the first computer programmer basically because she was talking to Charles Babbage about his machine. She thought it was the coolest idea she's ever heard. She had a lot of mathematics background, thanks to her mother, who made her had her take mathematics classes. And she realized early on that this machine that Charles Babbage was designing could actually become, like, you could use it to make it do a generic set of things. And she wrote a program about that. I forgot to get the link, but there's actually I'll forward it to everybody. There's a great blog post that came out about a month or so ago about what would her first programs actually do. And it's very fascinating to see like what kinds of things her programs did. Now, if you looked at what she wrote down, you might not recognize it as programming, but once you understand what she's targeting and the machine she's targeting, you'll see that, oh yeah, these really are programs. So she actually has a programming language named after her and is absolutely a pioneer. Okay, question 3, what's that? Carol, right, okay. Who here has taken 106A at Stanford? Okay, only a few of you, all right, about half of you maybe. That is this is how we introduce programming to the students at Stanford in the Intro Computer Science class, 106A. And it's we'll talk more about the details of that later, but one of the things we're going to discuss is like how do we teach introductory material to students and children and college students and all that. And one of the ways we do it is through, in this case, a little graphical person that kind of walks around a screen based on some commands. So we're going to talk about that. And if you haven't seen Carol before, great. You can do that part of the assignment where you get to actually play around with this, and it's kind of fun seeing it for the first time. Okay, that's what Carol is. All right, question 4. What British mathematician worked at Bletchley Park? This is the one I mentioned a little earlier. World War II, is a giant in theoretical computer science and has the Nobel Prize for Computing named after him. Alan Turing, right? This guy. Right? Not quite this guy, although he played Alan Turing in a movie. In fact, it was a great movie, The Imitation Game. If you haven't seen The Imitation Game, watch it. I'd say it's great. It's a good movie. I mean, it got very good reviews. I thought it was great, knowing what I know about computer science. This is actually Alan Turing, and he really is a giant in computer science. He was at the forefront of the theoretical computer science about what kinds of programs can we actually write? Like, what kinds of things can computers solve? And are there any problems that computers can't solve? Right? And it turns out, spoiler alert, yes, there are lots of programs computers can't solve, and we'll talk some about how that came about and so forth. Alan Turing was, as I said, he was one of the ones leading the breaking of the Enigma code. His computer that he built was part of that effort. And he also was happened to be homosexual, and in World War II, that was not a thing that was very well received in Great Britain, or for that matter, all around the world. And he actually committed suicide based on having to kind of not really out himself, but being involved with some things related to that. And it was very sad. A couple of years ago, the British government actually formally apologized to his family and to him about that, but it's kind of a sad postscript to his life. But as far as mathematics and computer science is concerned, absolute giant in the field, and we will talk more about him as we go along. And I'm sure Dr. Enigma will also mention him. And if you haven't seen the movie, you should go see Imitation Game, because it's great. Okay, here's another one that maybe some of you know. A couple of you electrical engineers might know this. whose master's thesis on digital circuit theory has been called possibly the most important and also the most noted master's thesis of the century? Yeah, I would say it a little louder.
Shannon.
Claude Shannon. Is that what you're going to say as well? Yeah, Claude Shannon. So this is the guy that invented information theory, right? Now, information theory is how we actually communicate using ones and zeros, basically. He said, wait a minute, we can take Boolean algebra and relate it to circuit theory for switching, and oh my gosh, look what we can do. We can do all these amazing things with computers. And he came up with that in MIT when he wrote his master's thesis. And it really revolutionized computing in general because that was the first time people said, whoa, we can do ones and zeros. That's all we need is really what it comes down to. Okay. All right. Who is known as the grandmother of COBOL by popularizing the idea of machine-independent programming languages? You'll take a guess.
Grace Hopper.
Grace Hopper, exactly. Who's heard of Grace Hopper? Few of you. More of you should hear of Grace Hopper. First of all, she was in the Navy, so you should all absolutely know who she is. She is another giant in the field. She was not only was she in the Navy, she was a mathematics professor during World War II and decided that she wanted to join the cause for the war. So she went and joined the Navy. And she ended up, they said, wait, you've got all this mathematical skill because she's a math professor. We're going to assign you to Harvard University where they're working on the Mark I computer, which is going to be used for figuring out how to drop bombs and how to do various other things that they needed computing to do at that point. And so she worked on that, and while she was working on that, came up with a lot of ideas about computer programming languages and about COBOL. Still, Ben's going to correct me if I'm wrong, the most widely used, or almost the most widely used language in the world, which you've probably never written one line in.
Yeah.
Correct?
No one's writing new software in COBOL, but people who know COBOL have easy jobs because banks are still using COBOL programs from like 50 years ago.
Mm-hmm. One of the things about banks is they don't want to change things that are already working. And so they wrote these programs in COBOL 50 years ago, and they just have kind of brought them through. Most of you guys were probably, and gals were probably born before the year 2000, I'm hoping. Some of you weren't, maybe. There aren't any sophomores? Anybody born after Y2K? You guys probably, maybe many of you don't remember Y2K, but Y2K was this, it took the world, like, it scared the world, was what it was. And in about 1997 or so, I remember first hearing about it, was it turns out that many of these programs, many written in COBOL, because the amount of memory in your computer, in the computers of the day, was so small, they decided to use only 2 digits for the dates. So the date was like 89, 90, 91, 92, 93. Well, there's a problem if you get to 99 and then go to 2000. 1999, 2000, you end up going from 99 to 0, and all of a sudden your code may explode because you've been comparing dates on various transactions and things, and the computer says, wait, there's a negative number here, the date is wrong, whatever, and it was a big, big deal. Turns out that they figured this out. Nobody really thought about it until about the late 90s. 97, as I said, was when I first heard about it. And there was this mad scramble to either fix banking programs in particular or other programs that ran the stock market and the missile systems and all the other things that are like pretty critical. Had to fix these things. Many of those programs were written in COBOL. And so people who had been in retirement from programming COBOL all of a sudden found employers calling them up going, we will pay you $300,000 a year to come fix this program so our computer doesn't die. So it was like really, really lucrative. So so you never know. If you do a lot of Java now, maybe 50 years from now you'll have to do that. We are facing another issue coming up. It's called the Unix Epic, which is Linux, which many of your computers might run, or Unix, which your Macs run, happen to use a they use a specific length of number. And if you've been in 107 or 107E before, you know that there's 64-bit numbers and there's 32-bit numbers. And the Unix epoch is a 32-bit number, which means that it only goes up to 4 billion. And it means that like every nanosecond, it counts up another digit, and it will also wrap around, and that's what's used for the dates on a lot of computers these days. So we're facing the exact same issue. I think 2038, I believe, is when we're going to face that again. So find out what all the programs are written in now and get ready for it. 2038, come out of retirement. You guys won't even be retired then. I might be, but you might not be retired. Anyway, Grace Hopper, giant in the field. In fact, starting this week, just because it happens to be this week, is a worldwide conference dedicated to Grace Hopper. It's called the Grace Hopper Celebration. It happens to be in Houston, Texas, and it celebrates women in computing. Excuse me. And I went once, and it's amazing. It was like 10,000 women and Chris Craig, right? But it's mostly women who go to this, as you might imagine. But it literally is 15,000 people these days go to this conference, and it's just if you happen to get a chance to go to it someday, it's awesome, and it's just a great place to see so many women involved in technology. Yes. Very good question. So a machine-independent program means you write it for one type of machine, and you can run it on a whole different bunch of machines. We're going to start to get into the idea that there are very machine-specific languages, namely machine code and assembly code, that are not what we call portable. COBOL is more or less a portable language. You run it on one machine, and you can translate it over and run it on some other machine without rewriting the code. Good question. All right. Next question. Okay. I have up here a whole bunch of programming languages, some of which you may have heard of, some of which you may not have heard of, okay? You've probably heard of C++, you've probably heard of Java if you've taken any of the intro classes here. You've probably heard of Python, and you may or may not have heard of Pascal or Scratch or Ruby or whatever you may have. But I'm just curious, does anybody know when these languages were created? If you've never heard of one, you might not know. But let's just start with Pascal. When we get to the one you know, let's go with it. Okay. What do you guys think? So here's the history of Pascal. Or not the history, but I'm going to date myself again. But that was the first real language other than BASIC, which I learned when I was a kid. So if you can figure out how old I am, maybe you know roughly when it was created.
70s.
What's that? 70s. There. Whoop. Very good. 1960s. So it's close. 70s. I guess 70s is when it kind of became a little more prominent. So I'm not quite that old. Okay. How about Python?
90s.
Yeah. What do you think? 90s. Yeah. Python's a pretty relatively new language. Now, it happens to be most people consider Python these days to probably be the most widely used programming language, right? We are now, last quarter actually, and the quarter before, we've piloted a 106A Python version of the 106A curriculum because we kind of realized, hey, everybody's programming in Python, probably not a bad idea to learn it. It's a great language. If you haven't programmed in it before, it's relatively easy to learn. It looks like pseudocode. It's got a lot of things built in, and it's a very, very nice language. How about BASIC? 50s or 60s, yeah. This is another language, 1960s as well. This is another language that I remember programming when I was a kid. This is a language that these days nobody really, that's not true. BASIC, there is, what's it called? BASIC, not Turbo Basic, what's it called now? I forget. There's a BASIC, VB Basic, or Visual Basic, yeah, Visual Basic, that is still fairly widely used. But that was a language that if you bought a computer, like a personal computer, in the early 1980s and late 1970s, when you turned it on, you were immediately programming in BASIC, whether you knew it or not. So you would turn it on, and it would immediately go to a little prompt that said "ready." And if you had the manual, and all computers came with an actual paper manual back then, you could program in BASIC immediately. And millions of kids got involved with programming because they turned their computer on and it didn't do anything else except say, "Hey, start programming me." Right? And this is not really the same these days, right? I mean, that's not true with your phone or with your iPad or with your computer. Now, personally, I think that that may change if we pitch it right, you can actually do programming on your computer or your phone right now using which language that's up here?
JavaScript.
JavaScript. Yeah, there's a language, JavaScript, which is web-based, and you can do that, and you can turn your computer on right now and program in JavaScript right off the bat relatively easily. It's not as easy as just it comes up and there it is, but you can do that. So I think that may be very, very important in the next decade or so for kind of teaching kids about programming. We'll get into more details about that. Anybody ever heard of Algol? Yeah, a couple of them. You've heard of it? Yeah. Algol. Okay, so if you haven't heard of it, was it probably created recently? Maybe, maybe not, right? I could be, there's maybe some up here that you might have not have heard of that are. But Algol was an older one, 1950s. It's one of the older languages, along with COBOL and along with Fortran, which is next on here, so I'm giving away that a little bit. But it was one of the languages that if you programmed in C or C++ or Java or JavaScript or even Python, it has its roots in Algol. So Algol, almost more than any other languages, Fortran could probably claim that as well. Algol is really the structured programming language that birthed all these other languages. So kind of interesting there. Okay, how about Fortran? That's old, yeah. Fortran is another 1950s one. Fortran was a programming language. Now, believe it or not, if you go to the physics department over here, you will find lots of physicists who still program in Fortran because lots of libraries were written for Fortran way back in the day, and they still work. So why try to recompile them for some other recreate them for some other language if you've got this mathematical program that already works? Why do it? It's kind of the same idea with the COBOL, right? Don't change anything that's broken. But it's not the best language in the world, right? I mean, we've had another 75 years to figure out how to make things better. So, but people still do it, and you can still do that. Okay, how about JavaScript? Any idea when that was created? 90s, yeah. So JavaScript was created in the 1990s. Now, here's how that happened. JavaScript was, it's the language of the web. It's an actual programming language that runs most of the things that you get on your screen, particularly all those little pop-up boxes that are really annoying with the X that floats around and you can't click on it and all that. That's all JavaScript, right? And JavaScript was invented because Netscape, which was a huge browser back in the early 90s and late 90s, decided they wanted to be able to have a programming language so that you could program with the web. And so they said, oh, let's come up with a program. And they called it JavaScript because Java had already been created. We're going to get that down here. And Java had already been created. And they said, oh, let's make it sound like Java because that's kind of that'll give it some immediate credibility, which is kind of a dumb reason. It's not the same as Java. It's different. They look similar because Java and JavaScript both have C syntax. So they look similar in that sense. But they are completely different languages. The guy who created JavaScript was given, I believe, 2 weeks to write the language, and he said, well, he's already written a lot, like he'd already done programming language writing before, but he said, and he wanted to make it much more like a different language up here, Lisp, and they overruled him. They said, no, Java's the new thing. Let's make it more like that. And he said, oh, all right, but he did sneak in some interesting parts to it that actually are very similar to Lisp and some other what we call functional languages. So JavaScript is a language that you can do not just what we call imperative programming, where one line comes after the other, but functional programming where you can have objects that don't have what we call or they don't change the state of the whole system, and it's an interesting way of programming, and he built that in there. So we got the benefit of JavaScript. The problem with JavaScript is it's not really, he had 10 days to write it, it's not the best language in the world for lots of reasons. If you go and look at the JavaScript book, like JavaScript Nuts and Bolts or whatever, it's like that thick. And it's got everything you ever want to know about JavaScript. There's another book that was written a few years ago called JavaScript The Good Parts, and it's about that thick. And you can actually program almost anything you need to do in JavaScript using JavaScript, the good parts only, and it's actually a very beautiful language. So the other class that we're piloting right now, in fact, Jerry Kane is teaching it this quarter, is 106AJ, which is a JavaScript version of 106A, and the students love it. They think it's a terrific course. So that's coming up as well. And I mentioned I think JavaScript's a language you'll see a lot of in the near future. C. How about C? That language. Yeah, so I've heard 60s, I've heard 70s. It is actually not as old as you might think, even though it's very prevalent. It was the 1970s, and that language, we were talking about machine-independent code before. C is the first real programming language that really was portable across many machines. And not only was it portable, but it was fast. And it was built such that it's very low level for what it does, but it is still a high-level language. And if you took 107E or 107 or some other classes, you know a lot about C, and you know some of the frustrating things about it. Hard to manage memory, right? Easy to have buffer overflows, lots of issues about that. But you can also do things very, very efficiently in C, and it gets translated into machine code very efficiently, so that you can do that. And what they built it in the 1970s because they had these mainframe computers that they wanted to be able to build operating systems for, namely Unix, which is built in C. They wanted to build Unix and use it on a PDP-11 and also on an IBM something or other and also on some other machine. So they built it specifically for that, and it took off, and it really is it's almost the most important. I would say it's probably more important these days than any of the other languages in terms of like doing something on a machine. Your phone has a lot of C. Your computer obviously has a lot of C in it. All the little embedded devices in your house. If you have a router, wireless router, the language that's been coded in is probably C. Your car has probably 200 computers in them. Most of those computers, somebody coded up C to make those do things like deploy the airbags and have the brakes work right and all that kind of stuff. So it's very much used in embedded systems. Double E's do a lot of C as well. Do VHDL and things too, but a lot of C. C++, when was that invented? Yeah, 1980s. So Bjarne Stroustrup came along in the 1980s and said, oh, C could be better. C could have this cool thing called objects in it. And he actually created a language called C with objects and then changed it to C++, which of course is a joke on C because C++ means one more than C. And that was created in the 1980s. This is the programming language that today is used for virtually any game that you see, other than the ones on your phone. If you have a game on your PC, it was probably written in C++ because it takes all of the good things of C in terms of being fast and makes it so it's easier to write big, robust programs. That's where C++ came in. How about Java? When was that created? 80s or 90s. I like that. Yep, it was the 1990s. It was in the late 90s or the early 90s. Well, kind of mid 90s. Java was the language that was supposed to be able to run your toaster. Like the people that created Java said, we want to be able to build a language that is very safe. In other words, you can't go and muck around directly with memory. And it's also going to be the kind of language that we want to proliferate through every machine possible. And it was also going to be the language of the internet. People thought that it was going to be in terms of Java applets, which are kind of like programs that you run on the internet. But that just kind of disappeared. There were some security issues with the internet related to that, and JavaScript really took over that hat there. Okay, COBOL. We talked about COBOL a little earlier. When do you think Grace Hopper was writing that? 50s is another old one. Yeah, okay. 50s is really when the first languages kind of came about, right? The first high-level languages, anyway. That's that. All right, Lisp. Who's heard of Lisp? Yeah, question.
Is there any reason why they all have these, like they're all written in caps? Does each one?
Yeah, good question. Some of them are in caps, some of them aren't. I think the caps is probably mostly just because that's the way they did it back then, and they said. Now, some of them are also acronyms for various things as well. COBOL, acronym. Common business-oriented language. So yeah. Fortran. I think it's. Yeah, what is it? Formula translator. Yeah. So there you go. So a lot of them are kind of acronyms or like words stuck together or whatever. Some of them are, some of them aren't. Okay, Lisp. Lisp is in it. Yeah. What do you think about Lisp?
I just know that like Polygram is like super.
It's what?
I just heard that Polygram is super related to this.
Oh. Yeah. The programmers, you mean?
Yeah.
Yeah. Well, Lisp is another language that was Any ideas when? 70s, 80s, 60s. This is another old one, right? It was actually invented by John McCarthy, and he invented it at MIT in the early 1950s, and he invented it because he was trying to. It's the first real functional programming language, and he invented it because he was doing research, computer science research in artificial intelligence, and it was a huge language that started kind of the AI revolution. It actually led to some of the AI revolutions like downfall in some sense when it became when they realized that Lisp wasn't quite up to the job to be fast enough to do some of the processing and given the computers of the day. That was it. McCarthy actually moved to Stanford and was in the department, CS department here for many, many years. If you go to Gates, you can see his picture up on a couple of different billboards and things. Swift. Who's heard of Swift? For you guys, what do we use Swift for? iOS and also Mac OS. But it's like, any idea when it was created?
2010s.
Yeah, 2010s. It's very recent. I think it might be the most recent one up here. So Apple had another language called Objective-C, which is a little like C++, a little like C, a little like Lisp. It's kind of a different language. And then they decided we're going to make things a little easier for people to go program. And they came up with this language called Swift. I think it's a pretty good language. If you've programmed in it before, it's decent. It's fast. It's easy to write in and looks a little like Python. It's not bad. How about Scratch? Who's heard of Scratch? Yeah, when was Scratch invented? Any idea? 2000s. I like it. Yep, Scratch. What's the deal with Scratch? Like, what's its kind of big thing? It's visual. It's for teaching kids most of the time. It's a language that is what we call block programming, where you drag blocks to make loops and you drag things around, and you don't have to type much. Right, which is a very cool part of the language. And we are going to spend a little time when we talk about Carol also talking about Scratch, and our assignment is going to be based on Carol Scratch.
Is that weird too? Because I don't know if anyone has messed around with Unreal Engine, but Unreal Engine actually has like a visual program. Like,
Unreal Engine does have a visual
like
program.
there's also like the standard like C++ programming one, where I guess if you want to do more in-depth stuff, but for basic stuff, there's like a visual program and stuff. So maybe visual. Like stuff like that where you drag blocks around just sort of connect them to do like loops or things.
Yeah.
Well.
Yeah. It's there are other exactly. Unreal Engine and other things have jumped on this idea of block programming because it's not too hard to do for people, especially people who have more of a I'm designing a game and less of a I'm doing a program sort of idea. So Scratch is interesting. Scratch is actually an excellent language. One of its issues, I think, is that it looks so cartoony that it's like kids will love it when they start it, but then they'll get to be like, let's say 12, 13 years old, and like, I'm not going to keep programming that. That's for babies, sort of thing, right? When if they only realized that you could make very good programs with this, and if they kept going past the like, oh, it's a cartoon and comic-y sort of kids thing, they'd actually do it. All right, how about C Sharp? Oops. How about C Sharp? Anybody heard of that one? What do you think?
I had a book on it in the 90s.
Okay.
It might have been the 80s. I want to say 90s.
If you had a book on C Sharp in the 80s or 90s, you probably would have had to work at Microsoft because it was actually invented in the early 2000s. So I'm not sure if you're thinking of some other one or whatever, but yeah, C Sharp is interesting. C Sharp is a language invented by Microsoft for the .NET system, which is basically what all the Windows computers run now. And it was invented as a direct competitor to Java, meaning that it's a safe language and it's very robust and has lots of libraries and things. But it was written because Microsoft didn't want to use Java because they didn't want to have somebody else like running the show. They wanted to run their own. So that's what it is. I happen to think it's a very good programming language. It just happens that you can really efficiently only use it on Windows machines, and not everybody has Windows machines. So I think that's one of its downsides.
C-sharp.
What's that?
Ironically enough, Unity uses C-sharp.
Unity probably does use C Sharp, at least the Windows one. Yeah.
The Mac one does too.
The Mac one does? Oh, okay. There are some C Sharp open source ones, but mostly it's Microsoft.
I think Microsoft also open sourced it too now, right?
Yeah, they do.
Oh, they did. They open sourced it. I didn't realize that. Cool. Perl. Who's heard of Perl? Yeah, anyone know when it was invented, roughly? Yeah, well, it was actually the 80s. Yeah, it's kind of an old language. Perl is kind of known as a write-only programming language. Its syntax is like ugly, and it is, if you can write things very tersely in many different ways, and you can get it to work. It's the language that was used for the back end, and still is used for the back end of many websites these days. So you can also use JavaScript, or you can use Python or whatever. But Perl was running the internet from all of the 1990s. But it's a hard language to kind of keep up. It's a hard language to write and like understand because it just wasn't written with that in mind. Assembly language. Assembly language? Any ideas? 50s? How about the 40s?
Yeah.
Now, this one is, so if I had said machine language, we could have said the 1800s because Charles Babbage actually did that. Assembly language is taking textual representations of the machine code and being able to use that. And that was mostly 1940s is when that came about. Back then, the only way to program your computer was in the machine code, and they decided they wanted to do that. Okay, who's heard of Ruby? Ruby, yeah? Any idea when it was invented?
90s.
90s. Yeah, 90s was when Ruby was invented. It's another language that is very similar to Python in the sense that it's object-oriented. It's very easy to write in. You can use it for the web. You can use it to write big programs, whatever. It kind of had a little weird trajectory where it was really, really, really popular about 10 years ago, 7 or 8 years ago, and then just shoop, kind of fell off. I think more people went over the Python route and JavaScript route at that point. And then PHP. What famous website was originally written in PHP? There are probably a lot of them, but there's one really famous one. What's that?
Wikipedia.
Wikipedia has a lot of PHP in it, but Facebook is the one I was thinking of. Mark Zuckerberg back in I gave it away. 1990s. Mark Zuckerberg was in the early 2000s. This was the language of the back end of the web as well, and Perl. So it allows you to do lots of web-based things, and Facebook still runs a lot of PHP. Those are a lot of big ones. There's a lot of languages on there that we didn't see. There are thousands of programming languages. I just happen to pick a few in here that are, I thought, interesting. There's a couple other languages that I think you might want to think about at some point, like going and reading about. There's one called Haskell, which is a functional programming language, very research kind of oriented. OCaml is another one that's kind of also got that research aspect to it. But those are kind of the biggest ones. R is another one. If you're a statistician, you've probably used R before. Many people are transitioning to Python now because Python has a lot of the same libraries, but you can still program lots of R. Okay, that was a long game. All right, here's another kind of game. Top left, what is that computer? That is the difference engine. That's the Babbage difference engine. Okay, not that you have to know these things, by the way, and I wouldn't expect you to necessarily know these things. How about, I think I go this way. The Mark, well, how did you know that? Well, I went down the other way, sorry, we'll get up to that one. This one's the bomb from Bletchley Park. That's the one that Alan Turing was involved with. This one, not quite Mark 1, but this is the ENIAC. That was the computer at University of Pennsylvania in the 1940s, the first big army computer that calculated bomb trajectories and things. And it was really the first programmable computer and you program it, by the way, by doing all these plug things. And it was slow, but it did the job. And it did the job better than humans could do the job, at least faster. How about this one down here? Yeah, you can kind of see right there. It says IBM. It's hard to see from way back there. That's it's an IBM System 360, kind of the workhorse of the 1960s and 70s computer. So those are kind of the big those are like some big ones that you would have seen in various old movies and things. Okay, how about some other ones here? How about this one over here? That's an interesting one. Probably don't know what that is. That is the Xerox PARC Alto. Now, why would I bring up some weird computer that looks like that called the Xerox PARC Alto? That computer is the grandfather of the Apple Macintosh computer. In other words, it has a graphical user face, and notice this. That is the world's first mouse. Well, more or less. The world's first mouse there. And it had a graphical user interface, which is exactly what you use today. So your computer today is based on that Xerox PARC Alto. And PARC is the Palo Alto Research Center, which is was, at least back in the day, very much tied in with Stanford and Palo Alto and research in this. And a lot of cross-pollination between Stanford and Xerox. And it could have taken over the world. They didn't market it very well. It was too expensive, and they just didn't market it very well. And Steve Jobs went and took a tour there one day and said, "That's my next computer." And next thing you know, we have the Macintosh. So, yeah. So thanks, Xerox PARC Alto. Okay, how about this one?
That's the one that Bill Gates made BASIC for. Right?
Yeah, this is the Altair 8000. It says right on there. I think that's, yeah, there we go. Exactly right. Say it a little louder.
That's the computer that I think Bill Gates saw in the front of a magazine and then went and made BASIC for it.
Yep, the Altair 8800 was really the first kit computer you could buy, and it you could put it together, and it came in a bunch of parts, and you'd solder the parts together, and you'd do it, and then you had a computer, and you actually had a computer with a microprocessor in it, and this was glorious to like the hackers back in the late or mid 70s because it didn't happen. You couldn't get it. And it was like less than $1,000 or maybe $2,000 to get this. I mean, it was relatively speaking inexpensive to have a computer on your desk. That was like mind blowing back then. And yes, Bill Gates saw this on the cover of Byte magazine, went running across Harvard Yard to find his good friend Paul Allen, and said, "We're quitting Harvard right now and going into business. This is the next biggest thing." And they did exactly that and ended up writing BASIC for this computer and ended up working for the company, and then, of course, started Microsoft, and the rest is history. That was that one. How about this one? I think we go to, it might be this one. One of these two. I won't push the button until next. What's this one? Apple II, right? That's like the computer that Steve Jobs and Steve Wozniak created. Wozniak really did the heavy lifting on that. Back in the day, that started the home computer revolution, really. I mean, this one was kind of, by the way, to program this one, you flipped little switches here for each number, and then you hit a switch that said that's number one. Then you switch, it was in hex, or actually binary. And you did binary, and then you did the next number, and next, and it took like half an hour to program. Bill Gates, they had a little loader that would able to take it off paper tape, so he didn't do that by hand. But that's the way that people who first got that were able to do it. So kind of cool. All right, there we go. Apple II is down there. How about this one? Yep, tough. That's the Osborne 1. It's the world's first luggable computer. All right, now what do I mean by luggable? It has a little monitor built in that's literally like 4 inches, right? It has a couple of disk drives, and it has some space to put your floppy disks in there to hold them there. And it's got like a modem that you can attach to it, which connects to the to other computers if you want to. And it's got a keyboard, and the keyboard folds up. It was designed to fit underneath a airplane seat. Or maybe probably not under, but probably in the overhead compartment anyway. And it was a like portable computer. Like this is the grandfather of the laptops that you guys are using, right? It did not have battery power, right? You did have to plug it in, right? And it weighed like 45 pounds. So it was, whatever. It was not easy. Okay, how about this one? Yeah, you can kind of see the IBM logo. I blurred it a little bit there. This is the IBM PC. This computer is the one that started like, it didn't start the home computer revolution, but it was the computer that if you were at a business in the 1980s, you had one of these on your desk, and there were hundreds and hundreds of them. IBM, which used to be building giant mainframes, in the late 70s said, uh-oh, we're going to lose this computer market if we don't do something about it. And they went and got commodity hardware, which means that they just kind of took off-the-shelf components, built this IBM PC, bought the operating system from a little company called Microsoft, that didn't have an operating system, by the way. They went and bought it from somebody else and then renamed it Microsoft DOS and PC DOS, as it turns out. But this was the first business computer. This was not graphical based. It was all keyboard. They had all these function keys. You had to learn all the different function keys. And if you grew up in like the 80s and used one of these, like you knew all the key combinations and so forth. It was kind of a bit boring. It had 4 terrible colors, like cyan, magenta, like brown, and red. I mean, it was terrible colors if you had the color monitor. Most people had just a green monitor. But it was very prevalent because businesses trusted IBM, and they said, well, if IBM's doing this, we're going to buy that. And they bought millions and millions of them. And so that's when IBM kind of started crushing the likes of Apple and Commodore and some of the other computers. But that's the big one there. So that's those are the big computers of the day. There are obviously lots of other computers. I could have put laptops on there, or the PDAs, or the iPhone, or whatever. But those were kind of the big ones I thought of when I said, "Well, what kind of things might people not know about?" I think that was that. Who's this guy? Don Knuth. Don Knuth is who? Like, what's he do? Yeah.
He wrote the big computer science book that had to do with all the algorithms.
Yes, this is one of the world's foremost algorithmists, and he wrote a book. In fact, it's a series of books. There's 7 volumes. He's through volume 4, and he just turned 80, so cross your fingers he gets through all 7. But he wrote a book called The Art of Computer Programming, and he happens to be, quote, the Art of Computer Programming professor at Stanford University. And talk about giants in computer science. He has been here since the 60s, and is named everywhere as one of the most prominent computer scientists. I actually was at a faculty lunch earlier today, and he comes into the faculty lunches. He rides his bike. He lives on the other side of campus. Rides his bike to school, wears his helmet all during lunch. And you're like, why are you wearing your helmet? One time somebody asked me, hey, Don, you want me to take your helmet? And he's like, no, I'll just forget it. So I'm just but he is great. He does a lecture every Christmas. He calls it the Christmas lecture. Does a lecture every Christmas, and is if you get a chance to go to it, I'll try to remember when it is near the end of. It's just about when finals are. Is when he does it. But he's still a terrific guy, and his brain is like this big. So I don't know how he rides his bike. But you should know who that is, especially if you might see him around campus. I was walking with some students a couple weeks ago, and he literally bicycled by, and I go, that's Don Knuth. And they went, huh, what are you talking about? And I went, that's Don Knuth. They went, oh my God, it's Don Knuth. But we didn't yell at him. We didn't want him to fall off his bike. Okay, that's he's a giant. You should probably know who he is. And if you see him around campus, you should marvel. He also invented this thing called TeX. If you're a graduate student, you might know what that is. Other graduates may or may not. It's a typesetting program. In the late 70s, he wrote one of his volumes for the Art of Computer Programming, and the volume was printed. Originally, it was done using lead type, which is the old way of printing, where somebody took a letter and put it on the page, and another letter and put it on the page, and did that. And then they finally moved to computer typesetting, and he got his book back, the print of his book back, and he took one look at it and goes, this is terrible. Looks terrible. They just hadn't figured out all the right algorithms yet. So he said, this summer, I'll make a better program. 10 years later, we had a better program, and it's called TeX, and you can write it, all your papers with it if you want, and it's he's won many, many awards for writing TeX. Oh, and by the way, he's also a Turing Award winner as well, one of the early Turing Award winners. So you should see it if you see him around campus. Okay, one of the things about this class, the end of this class, near the end of the class, to be announced when the date will be, I'm going to take all of you guys to the Computer History Museum. Anybody been there? It's in Mountain View. What do you think? Pretty cool, huh? It's a neat place. It's got a lot of these old computers. It's got these computers that look like this. I mean, who had a computer, right? It's got some giant IBM computer, and it's got all the console game consoles from all that. It's a pretty cool place to go and spend an afternoon walking around. So we will take a field trip down there. I don't know how we're all going to get there or whatever, but the red line goes kind of close, and we'll figure out how to do that. But we're going to take a little field trip down there. To see how it is, because it's right here. We're in Silicon Valley, and lots of the history actually happened here. So that's that. Okay, we have a little bit of time to start talking about some of the details of Charles Babbage and his machines. Charles Babbage, as I said, he's fascinating. He was the earliest pioneer thinking about computing. He thought, hey, I could actually, create a machine that uses steam, like this is the original steampunk guy, create a machine that uses steam to actually calculate mathematical tables. And he created this one called the difference engine, one of them called the difference engine, and he created an idea for another one called an analytical engine. He never actually produced either of them. It turns out that he just didn't quite have the mechanical tools and skills to do it. Now, I'm going to show you a little video in a few minutes, although I didn't connect it to the thing, so we'll see how loud it is. But they're talking about some people recently have created one that actually does work according to his specifications, and it's awesome. I'm going to show you the video in a second. Okay, here's what it looked like. I showed you that picture a little earlier. Okay, this is the picture of the one that was created in modern times, and he created a working model of it, but it didn't quite. It didn't do the whole amount of the calculations that he wanted to do, and it was very popular. Like people were like, wow, this is really cool, and it was a cool thing for back then. Okay, here's a model. Oh, sorry, this one was an original. So they made it out of metal, and it was all gears, and it had cool numbers on it. Very cool looking things. This one was given to London Science Museum, and then he created a difference engine number 2, and this is the one he didn't create. But let me play this for you, hoping it'll be loud enough. Hear that?
The engine behind me is Babbage's difference engine number 2, designed by Charles Babbage, an English mathematician who is also known as the first computer pioneer. Babbage designed this machine between 1847 and 1849. Babbage, as we know, did not succeed in completing any of his own engines in their entirety. So there is no complete Babbage engine. This is the first physical realization of any of Babbage's complete designs in the metal. The engine itself weighs 5 tons. It consists of 8,000 parts made of bronze, cast iron and steel, and it measures 11 foot long and 8 foot high. It's operated by cranking a handle. What it does is it calculates and tabulates the value of any 7th order polynomial, a class of mathematical expressions, to 31 decimal places. It not only calculates that with unerring accuracy, it also prints an inked hard copy as a record of the results, and also produces what are called stereotype plates. That is, it impresses the results in soft material, plaster in this instance, so that you can make a printing plate automatically. Now, the purpose of all this was to eliminate the risk of human error in the calculation and production of printed mathematical tables. The machine is operated by cranking this handle. So you turn this handle, and each cycle of the engine, the machine produces one result. So you just keep cranking. You set the initial conditions up on the figure wheels, on the numbered wheels, you turn the handle. What happens when you turn the handle is it drives this cam stack. And if you like, this is the microprogram. This is the device that orchestrates all the internal motions of the machine to get it to form the repeated additions that are needed for the method of differences, which is the principle it is using. So you turn the handle, it turns these cam stacks. There are 28 separate cams, and that is what determines the internal timing and the orchestration of all the mechanical movements of the whole machine. So that's, if you like, the guts of the machine, the internal microprogram. And what the machine does is it adds a 31-digit number on one column, and it progresses through the machine, adding from column to column to column, and the tabular value, the result, ends up on the very last column, 31 digits. So you crank the handle, each cycle of the engine, that's 4 turns of the handle, each cycle of the engine produces the next result on this column. So the end process, the end product of that whole process, is a 31-digit number on this column. So we take the 31-digit result from the end of the machine at the end of the cycle, and it is automatically transferred to this apparatus, which is the output apparatus. It does 2 things. It prints on hard copy, in inked hard copy, a 31-digit result. That's a checking copy, so that you know actually what you've calculated. At the same time, it impresses results on soft material in these trays. So inside there are things called stereotype punches, which are number wheels, which are lowered into the tray. The tray then moves, it lowers again, and so the lines build up. Firstly, it's on display here at the Computer History Museum for 1 year. It's on loan from the owner of the machine, which is Nathan Myhrvold, who commissioned the machine. He paid for the machine to be built. And so it's here for a year, and then it goes into his private collection. What we will do with it is demonstrate it for people. We'll work on it. It's a research machine, so it'll be adjusted and worked on. We'll get experience about how the thing operates. And also, part of the reason now that it is here and it does work, and we have for the first time a Babbage engine, the idea is to do some research and to say, was it a practical proposition? If Babbage had one, could they have successfully produced tables? Babbage was not an impractical dreamer. This machine works as he intended to work. But was the entire enterprise of using the infallibility of machinery to produce printed tables, was it realistic? Could it have been done? And for the first time in history, we were in a position to actually answer that question.
That is a cool machine. This guy did not think small. 31-digit numbers, right, with a printer in like 1870. Like, it stamped the answers on there, and that was really cool. So so this guy was not speaking now, not like thinking small. What are these differences we're talking about here? Okay, what happens is, so as he said, this thing can calculate polynomials, which is actually like the answers to polynomials, up to 7th order polynomials, which is pretty darn cool. Here's how it works, and it's actually very, very clever how it works. If we take a set of, let's say you're trying to create a table of squares, okay? 0 squared, 1 squared, 2 squared. If you figure these ones out on your own, you want the machine to be able to continue and figure the next one, the next one, the next one. Okay, so you have these ones. What you do is you take the difference between the answers to the first, second, and third one. So, for instance, we're going to do 1 minus 0 gives 1, and 4 minus 1 gives 3, and 9 minus 4 gives 5, etc. Okay? What do you notice about these numbers? They increment by 2, so if we take the next difference, what do you think we get? 2, right? And it's all the same. And if you did one more, it'd be zeros, then it'd be zeros from then on. Okay? Using this idea, what we can do is we can create a machine that says, okay, let's populate this with some initial conditions. And in this case, the initial conditions could be 0, 1, and 2. okay? And what it can do is then it can say, okay, using 0, 1, and 2, it can say, I'm going to add 1 to 2, and that gets 3, and 0 to 1 gets 1, and then we've got this column, right? And then you do the same thing again, and you get the next column, right? And if you continue, and you've got 4 and 5. 4 plus 5 gives you 9, and then you can get, I forget what I just said on that one, but you get the next one as well, right? So you do this, and it continues to do it, and that's what he did, built in, in brass or in metal anyway. That's how it works, and it's actually pretty darn clever. And this is that once you get to that constant, which you always will with a polynomial. That's the way it works, okay? If you always continue to do this, okay? If we did this with a series of cubes, right? Same sort of thing. Okay, now we've got cubes, and we do 1 minus 0, 8 minus 1, etc. And we get 1, 17, 37, 61, etc. And then you do the same thing again. Now we're not going to get the same, we're not quite going to get the same, but notice something about this. They all differ by 6, so when we do one more, we get to things. So in order to do a 7th order polynomial, you need to be able to do this process up 7 different times. But once you do, ta-da, you've got the answer to your, you've got the answer that you could plug into this computing machine and create these things. And they use this for creating tables of mathematical tables used in finance, used in manufacturing, used in construction, and all that thing that people were having to do by hand. And can you imagine if you've been doing 31-digit numbers by hand, all of a sudden being able to crank a wheel or hook it up to a steam engine and have it just crank away, crank away? Brilliant, right? Babbage could have been a multi-billionaire. He could have been the Bill Gates of his day, right? If he had actually figured this out. Now, you can do this using, you can do this for regular old polynomials, too. The same basic idea. Anyone have an idea how we might go through the process of figuring out how to do that difference engine using a polynomial like this? Think about it for a second. Actually, tell you what, take a minute, talk to your neighbor about this. Think about what you might have to do to get to like a similar table like we did before.
So what should it generate?
It's going to generate the solutions to this function. So we want the y value. We want the y value for if we plug in 0 or plug in 1 or whatever, what we get. Any ideas how we might do this? Like, what did we have to have before? What did I say we had to have back here? Jeez. Yeah, let's plug in some numbers, right? So what we could do is we could go and, hold on. We could plug in some numbers and figure this out, right? So let's do that. In fact, let me see if I can have my thing do this. So if, let's see, maybe not, hold on. Oh no, my pen's not working. Well, okay, maybe we won't do that. Okay, well, I will do it on the board. If we're going to do this, let's do the first one. Somebody figure out for me, if we do 0, what's x squared minus 5x plus 10? 10, okay, and then what's for x equals 1? 6, and let's do a couple more. X equals 2. 4, and x equals 3. I'm sorry, yeah, 1, 2, 0, 1, 2, 3. 4 as well, and how about for 4? 16 minus 20 plus 10. 6 again?
Yeah.
Let's see if we can figure out how this works, right? Okay, what are we going to do here? 6 minus 10, right? Negative 6. Okay, 4 minus 6? Negative 2. 4 minus 4, 0. 6 minus 4 is 2. Did I do it wrong?
Negative 4 for the first one. Yeah.
I'm a moron. Okay, there we go. All right. How about that? Negative 4. Okay. All right, now what we're going to do, we're going to do once more like this, right? Negative 2 minus negative 4. 2. 0 minus negative 2. 2. 2 minus 0. 2. There we go. So our initial conditions are going to be 10, negative 4, and 2. And we can plug that into the difference engine. And in fact, I have a difference engine up here. Okay, there it is. Okay, I have a difference engine up here, and what we can do is we can type 10, and we can type negative 4. I'm going to show you what that means in a minute. And we can type in 2, and if I clicked on the right place there we go. Oops, oh no, hold on. 0, there we go. There we go. So this is actually looks like this. It's 10. This is negative 4. Well, it's actually 9, 6. it like wraps around. Have you ever done like 107 or something? It wraps around. So that's what that means. And then 2. And we can hit the little step button on here. And what it will do, if I did this right, it will actually create the next one. So we started with 10, and it gave us 6. And if we click it, and how do we know it's 6? Because the last column over here says 6. Right? And if we do it again, it should give us 4. Oh, and it does. And what does it do to do that? It actually takes this number, it takes the numbers here, and does the difference like we did before. Or I guess it does it, adds them. And it does it. So if we keep doing it, and it, by the way, it prints it out up here as well. 6, 4, 4, 6, 10, 16, 24, 34, 46, 60. That's faster than you could have done it, right? So pretty cool. You do this a few times, and you can get there like that. Questions on that? What questions do you have about that? There is a link on the website. If you go to the website and then simulations, go to the analytical, the difference engine, you'll be able to play around with that a little bit. We'll talk a little bit more about that on Thursday as well. Could we do this for sines? How might we do it for sines? Can we put decimals into this thing? I don't think so. What could you do to make all these numbers not decimals? Yeah, multiply by whatever it is, how many 7, 10 to the 7th or whatever. Make that an integer, and then you start doing the calculations one after the other. Let me go here. I think I have it up on my screen. There it is. If I go over here, I did it up here, and I multiplied by that number, and then did the difference, and it doesn't actually come out where there's ever any sequence, like it never comes to 0. Why is that true? It's not polynomial. Like, that's part of it. If we extended this out a little more, we might get somewhere close, but it's not polynomial. So you can get pretty close. But remember, sinusoids go like this, and they're not polynomial, and this is only for polynomial sheets. Now, for 30 to 31, it's pretty good because they're so close, and everything at that range looks like a line. So you can actually get pretty close using this method. But it's not going to work for things like that. It's got to be work for sinusoids. Okay, so I tell you what. We'll do Ada Lovelace first thing on Thursday. What questions do you have at this point? About the class? About me? About difference engines? Yeah.
Random question. Why are you wearing a microphone?
Oh, we have a student in class who asked me to wear the microphone.
Oh, okay. I thought
Yep.
it was recorded.
No, well, that's actually a good point. I am recording a screencast as well. I normally try to record a screencast if I remember to. But I'd rather have you guys in class. Like, if you happen to miss a class, that's why I have the screencast. But
Okay.
I'd rather have you in class. Yeah. Good question. Yeah.
Is there associated readings with each class, and how do you
There is. If you go to the website, you can click on the schedule. I'll show you. Click on the schedule for the website, and it is, there we go. This is what the website looks like. Up here, we've got the schedule, and if you look at the schedule, it just says the Reader Chapter 3. So, and that's the Reader is located up here. Just click on that. Yeah.
In regards to those, like that calendar, is it like we should have readings done after that lecture, before?
It's up to you. Whether you have the lectures before or do the reading before or after, it's up to you. I'm not particularly worried either way. I think if you do them before, you'll already kind of know kind of the basic idea. If you do them after, you'll already have a little more to inform the reading. It's up to you. Yeah.
Could we come to office hours for this class and discuss about any of the?
Yeah, you want to come to office hours. I have office hours Tuesday 3 to 5, which is right after the class on Tuesdays. And I may not be holding it today. If you want to talk right after class, I'm happy to. But you are welcome to come by and talk about anything you want related to computer science, the class, or whatever. I think it will, like I said, the amount of work in here is going to be lower than a lot of other classes. So we won't see all of you guys like, oh my God, I can't figure out the homework. That part won't be the issue. But sure, absolutely come by anytime. Yeah. What other questions? Okay, yeah. The homeworks they're basically a set of questions generally that ask you to calculate the difference using the online tool to do this for a certain problem, let's say, and then talk about like some specific detail. Do you know any you remember that one? Like some of the details about that?
Yeah, so like the assignments, a lot of them go over like actually implementing the algorithms that we
And like I said, we're going to have different assignments, 2 assignments for a lot of the ones, so depending on which one you want to do. Anybody's welcome to either of them as far as I'm concerned. All right. All right. Hopefully we'll be able to figure out how to get this room cooler. And I look forward to having you all in class. If you're just shopping and whatever, thanks for coming today, and maybe I'll see you, maybe I won't, but I hope you guys want to continue along with the course. All right. I'll see you on Thursday.